Designing earthquakes is an investigation in which we change the Richter magnitude of earthquakes to see how that affects the likely damage. This stack of 20 pennies represents a very shoddily constructed 20-story building. We could investigate how different materials and different designs might make the building safer, but now we're aiming to design earthquakes which might damage or destroy the building. The hardware is a modified Math Machines function table which lets us shake the ground under the building in precisely controlled ways. Our software will let us control the motion of the shake table using a wide variety of algebraic functions. Here we focus on replicating actual earthquake waves as they were measured by nearby seismic stations. One option is the very powerful magnitude 8.8 earthquake which occurred off the coast of Chile in 2010. Another option is the magnitude 7.8 earthquake, which killed over 8,000 people in Nepal in 2015. A third option is the earthquake in Northridge, California in 1994, which killed 57 people and did over $13 billion of damage. We have several other options, including a magnitude 2.4 earthquake in northwestern Pennsylvania in 2016. The earthquake we're going to replicate here had a magnitude of 5.8 and occurred in Virginia in 2011. No one was killed, but among other things, this earthquake did enough damage to close the Washington Monument for 32 months of repairs. Each of these earthquakes is unique in its magnitude, but they are also different in other ways, especially their duration and the details of the shaking as shown by the waveform in each graph. The software lets us take each of the waveforms and change the magnitude. Our first trial looks at the potential impact of the Virginia earthquake on our shoddily constructed building if the building had been located directly above the earthquake and if the earthquake had actually been magnitude 0. Magnitude 0 does not mean there was no earthquake. When he designed his magnitude scale, Charles Richter thought that 0 magnitude would be too weak for detection by the most sensitive instruments, moving the Earth just 1,000th as far as the quakes which people might actually feel. In fact, modern seismometers can detect ground movements that are weaker than this, assigning them negative magnitudes. In our simulation, a magnitude 0 quake should move the table 1/10,000th of a millimeter. This has no significant impact on our stack of pennies or the honey-loving bear. Not even the laser dot we use to detect small movement shows any response to a magnitude 0 quake. If we increase the magnitude from 0 to 1, the maximum displacement from the initial position increases by a factor of 10 to 1,000th of a millimeter or 1 micrometer. That still has no perceptible impact on the pennies or the bear or even on the laser dot. Going up to magnitude 2 or 1/100th of a millimeter, there is still no detectable movement here, although a high-quality seismometer would easily detect a nearby earthquake of this magnitude. At magnitude 3, the maximum displacement again increases by a factor of 10 to 1/10th of a millimeter. Earthquakes at this level may be felt by some people, and our crude laser dot seismometer shows a little motion, but there is no apparent damage even to the very shoddy 20-penny building. If we go up to half magnitude to 3.5, the movement increases by a factor of the square root of 10 and moves almost 1/3 of a millimeter, enough to be clearly felt by our bear and to cause distinct movement of a seismometer, but there is very little, if any, damage. We'll change perspective as we go up to magnitude 4, making the ground move 1 millimeter. There is enough movement now that Pooh Bear certainly knows there is an earthquake and there might be some minor cracks beginning to appear in our building, but there is no sign of any serious damage. Magnitude 4.5 is a threshold where engineers begin to worry seriously about the possibility of significant damage to buildings, bridges, dams, pipelines, and other structures, and our shoddy penny stack is beginning to show some signs of slippage between the floors. Magnitude 5 increases the maximum displacement to 10 millimeters, and it might be disastrous for a poorly constructed building, especially if the building was damaged in a previous earthquake. We can try to simulate a magnitude 5.8 quake, the actual magnitude of the earthquake in Virginia, but that would require a displacement of 63 millimeters, beyond the physical capability of our shake table with the current gear. The distance the table is now moving is about the same as for our magnitude 5 simulation, and the bear has good reason to worry, but the biggest difference in the quake is probably the velocity and the acceleration of the shaking, not the distance as measured by the Richter magnitude. Velocity, acceleration, energy, and frequency are all factors which do influence the damage caused by an earthquake, regardless of the Richter magnitude.